Um, so we are back again today. I will share my screen. Share. Uh, okay, so yeah, we are in now in the second last meeting, and it is more on like a little bit of giving like a step back a little bit on the refinery, what they call like refinery wide optimization. And then these, in this case, it's so I mean the whole technique has been explained to you in the previous classes, um, starting from that RTO and sorry, the hydrocracking unit class, and then the what was it again, the RTO and then hydrogen pinch. And now it's about let's see how things are connected, as in the like a refinery or chemical plants or industrial plants. Yeah, so it's you can simply change this refinery into all kinds of industrial plants if you want. Yeah, so you can scratch this, making like a chemical plant or industrial plant wide optimization. So how do they do that? Because we know that plants are like very there are many recycles, and I mean, for people who don't understand the process and the plants, and then don't have yet the knowledge on, I mean, the skill on the process engineering is not that strong. So maybe the concept is very, I mean, the naming itself is very terrifying, but it's as simple as what I'm going to explain to you, basically. So you can read this, and then I recommend you to go through this because we're going to see this example. So you go to Gurobi. So Gurobi is one of the it's a company. It's also a name of a solver. And then I mean they claim to be like a fastest solver in the world. So you can then try and prove whether they are correct or wrong. So you go to that website, and then we will go through the examples that they are going to that they are showing in the website. So but if you go to that website, it's going to be, I mean, it's good for you for your optimization classes. So the outline for today would be the process network modeling. I'll show you a little bit what it means, and then this process network modeling, and then there are many things like I mentioned before. To solve this practically, it's very complicated. So we need to decompose the problems into I mean there are strategies to do that, and then this is then the what I meant previously by the simple refinery optimization case. So this is more on that Groby example. So we will go through that, and then this product network optimization. I'm not really sure. I think this is supposed to be like a debottlenecking stuff, but we will see. Yeah? It's a bit debottlenecking stuff. So I will give. I mean, you can watch this, yeah, but I'm going to skip it. So it's this video is basically, if you go to that AP Monitors website or YouTube videos. It's very good YouTube videos that you can learn how they do their things, and this is one of the examples where these students are basically intern in a company somewhere, and then they develop like a linear programming problems during that internship program, and then they use it to analyze and optimize the operation. So it's a very good example. So now let's do this. So if we see refinery, there are several things connected. Number one is then the oil liquid flows. Yeah, so we have the oils here, so crude, and then it goes to the distillation unit, and then we have this jet fuel, diesel, naphtha, and so on and so forth. You have seen this many times, right? Just to show you. So for example, this diesel, it goes straight to the blending station, and then jet fuel as well in this particular case. But we have also like a VGO in this case, the vacuum gas oil. And then it goes to the RFCCU, so what they call the like residue FCC unit, and then where it creates or makes from the out of this VGO vacuum residue, and then some gas oil from the delayed coker unit. It creates this gases in LPG, gasoline, and also the light cycle oil that goes to the hydrotreating unit. Yeah, I don't remember what this means. Maybe deep hydrotreating unit something, because this is like resid FCCU. So we have, so you have these oil pictures, all of these flow streams going through in refineries and also in your mine and in your chemical plants. And then you also have like what they call like an energy flow. So this energy flow, typically you will see that not as like a megawatt or megajoule per hour. You don't see these things. You see the ton per hour. Yeah, I mean, if you go back here, you see the ton per hour or kilobarrel per day in this case. So you see that, and then this one you don't see that kilobarrel per day or ton per hour. So what you see is basically the steam flow rate. So in this case, it goes to the steam, and then this is what they like a steam level, steam system. So we have this all of the steams are produced in this boiler, for example, and then it goes to this header. So this is what they call like maybe in this case 1, 2, 3, maybe 4. So this is a high pressure, this is a high pressure, yeah, and then this is a medium pressure, and then this low pressure, and then there is a condensate line, so to say. And then from this header, the steam goes to, for example, in this FCC unit. I don't know, maybe it needs to be to use for all kinds of stuff. Maybe to strip, for example, to strip out the light gases, as well as in the other units, hydrocracking, after hydrotreating, and so on and so forth. So and then there are some part of the steam that is then how do you call it? The pressure is dropped down, expand. Sorry, so it's expanded. So one is when some of the high pressure steam is expanded to the medium pressure steam level, and then in the next stage it goes to the lower pressure steam. So how much of these steams that are being let down or expanded, and then how you design these utility systems, it falls under your cogeneration course. So in this master's program, there is a course called cogeneration system. So you will learn, or you have learned maybe a lot on this system. Yeah. And then the things that we also discussed last time is the hydrogen flow, because hydrogen is very important in a refinery. And then typically they have like this it should be SMR, yeah? Steam methane reformer. So it creates it produces hydrogen, and it's used in 2 different units in this case. And then there's also like another hydrogen production, which is then this is a reformer. So CCR is continuous catalytic regeneration. So it's a type of reactor used in the reforming system. So both of these, they are producing hydrogen, each with different purities and flow rates, as you saw already during our class in the hydrogen pinch. And then you can design this. You can design how much goes to here, how much goes there, here and there, and so on and so forth, right? So basically, if we see all of these, the flows of liquid, the flows of energy, the flows of hydrogen, these 3 things are important. So we need to make a mass balance, yeah, to get that refinery wide or chemical plant wide in our head. So we need to be able to make the mass balance of the process unit, right? And then you also need to make a mass balance of the intermediate and then final product streams. So so you can see here, for example, so in each of these unit, you need to make the mass balance in and then out. Sorry, in and then out, for example, and it's also somewhere in between in here intermediate streams, or this one intermediate streams, and then where you need to make that calculation and the mass balance. Yeah, it's very important to establish that kind of calculations. Otherwise, without this mass balance calculation, we will not be able to do anything. Yeah, forget about improving your plant. You have to make the mass balance for your plant. And then we make a mass balance or energy balance for the utility. Yeah, mass balance in terms of like a ton per hour of steam, for example, or water or electricity in terms of like a megawatt hour or something. And then you also need to make a mass balance of hydrogen. So all of these things, they are interconnected. And then you can have like what kind of product specifications that you have to meet. If it's like a run number, is it like a pour point, is it like a flash point, is it like a vapor pressure, the RPP, for example, or is it like a purity, or is it like a density? So all of these things, if there are many things, but then if you like look at your product and then determine what are the most critical product specs that you have to meet. For example, the gasoline is obviously the round number. Yeah, there's no doubt about that. But then for the diesel, it could be like a C10 number, or I don't know, smoke point, for example. I don't know. And then for your product, for example, in chemical plants, we need to fulfill the density. Maybe we need to fulfill the purity. Yeah, those things. And then from each of these purity, and then from each of these, for example, let's take the purity. So what are the things that controls that purity? Yeah. So these things that control the purity, for example, these are that your independent variables, or it could be like not a completely independent variables. They are variables, but they are also dependent on other stuffs. Yeah. And then you could also see like a quality constraints on intermediate streams is the same basically on the product spec, and then some capacity limit on each process unit. So I hope that you get idea. If not, then let me know. So basically, what you need to do is then combine these three flow diagrams together in one big giant sheet, and then take into, I mean, consider only the most important streams and products, because you have the cost, you have the prices, and then you can then develop this on your own, and then understand how things are being connected, and understand how things are being operated. Okay. It's not like now I need to have, I mean, I need you to have it in your mind. This is not like a 1 week or 1 month job. Yeah, this is like weeks or months of jobs, and then depending on how big your plant is, how big your scope. For example, in this case, say for example, I'm not going to model the whole plant. Maybe I want to model this plant only, and this already, like for example, I don't know, depending on its complexity, it could take like several months or maybe several years to do so. Yeah, now showing you the concept and then how to do so, but then doing that in details, it takes again, as I mentioned in the RTO class, so it takes strong collaboration between you. I don't know what your position is. I mean, you means, if I say you, means you are the process engineer. So between you, process engineers, and then the process technology in the R&D department, and then the operations people in the maintenance as well. Basically, the operations people, the process engineer on the field. Okay, and then all of this data and the management as well, they have to be made full aware. And then once we get all of the mass balance, like I've been showing, like we have been seeing this more every classes, right? So once we get the mass balance, and then we can then, yeah, I mean, define so product sales, and then the material purchase, and then utility cost, and then the capital cost if there is any, right? So from here you can then sales, obviously, I mean, the profit is obviously sales minus all of these costs. And then you can also maybe if it's not like if it's like a running plan, for example, you can do it this way. So sales minus all of these costs, including the raw material purchase and then operating costs. Yeah, so it can be done like this. And then you could also ask, I mean, how do we get this? I mean, if it's like a new plant, how do we get this into the equation? Because you know that this is more like dollar per time, right, or money per time. So this is money per time. And then it's also money per time, money per time, money per time, but this is typically like only money, right? So it's only like the typically money, or okay, euro, your euro, or ringgit, I don't know. So these are typically money. So how do we then put this into the equations? Because this then basically ringgit per time. So what we typically do is that instead of like this profit, I mean, sorry, this capital cost, it's if we assume, for example, you have assumed like 20 or 30 years of operating, and then you have the capital investments, and then there are several ways on how to calculate the cost, this capital cost in terms of a year. So the easiest one being, like for example, if you have like a 200 million euros of plant, and then you divide that by 20 years. So 200 divided by 20 years means it's how much is that? 10, right? So it's 10 million euros per year. Yeah, 10 million euros per year that you have to pay for the capital cost. So that's very straightforward and easy calculations. And then you can use that as for this in writing your objective function. So once we get the objective functions, as you understand this already, because we have been repeating this many times. Then we can then answer the following questions, because these are decision variables. So we also call these independent variables. We also call these like features. If you are working in data science buzzwords, so they will then call these features. But nonetheless, this is what we know in chemical engineering as independent variables. And then we will then say, okay, we can answer the questions on which goods to process, which product to.
Sorry.
Yeah.
Your voice was cutting quite several times. I don't know is it only me or the others? Because your voice like cut in between for several times.
Oh yeah.
So I just want to ask. Yeah.
I don't know. Just let me know.
Okay.
Very good. Is it now okay?
Yes. Now you cut a bit.
Okay. Now I think I need to step forward a little bit. So yeah, which goods to process, products to produce, which operating route to use. For example, in this case, you can see this. So, for example, yeah, this vacuum residue. So, does it go to this RFCC unit, or does it go to delayed cocoa unit, or does it go to like a coke or something? So, just does it have to be like a disposed? So, all of these these are decisions that you have to be able to calculate given the cost, given the price, given the availability of the units, and then given the performance of the units that we can then generate from the data. What was it again? So also with which catalyst to select, yeah, and then operating mode, and then do we need to produce a maximum amount of gasoline, or maximum amount of diesel, or maximum amount of jet fuel? So these are the things that you can then steer the plant, or how to put it? Yeah, drive the plant into one of these three operating modes, for example. And all of these depends on the prices and the cost at the time that you do your optimization. So you make the model. That's the first one. You get the data, you understand the process, you get the data, you make the model. So that's like a one step. And then the other step is then make sure that you get the data correct, especially for the prices and stuff, because these are very dynamic. So and then getting the model is only like a first step out of the next 100 or dozens of steps, because the next dozens of steps is to evaluate the economic situations in such a way that you can maximize. I mean, you can capture as much as possible the dynamic, and then you rerun and run with these models, and then get some results which you can then analyze and then make your decisions based on that. Okay. So that's the I mean the in a nutshell how we do things. Obviously, when we model this, when we have this model, right? I mean, not everything's. I mean, not everything is linear. In fact, there is. I mean, everything is non-linear basically. So if it's everything non-linear, how do we then quickly do this modeling and optimization? One way is what they do, because when we have this non-linear, you understand this already from your optimization class. If we have like a non-linear system, it's relatively difficult to optimize or to solve. Yeah, it's very difficult to optimize to solve. And then even though, I mean, even when we have a solution, it may or may not be like the global optimum solution. So what we do is typically we step back a little bit. So we analyze the data, and we have to be able to make, or we have to make the problems or the models as linear as possible. Okay, as linear as possible. So this is what I mentioned. So we have this the process is then the bold line. So it's then the process, just an example. Yeah, and then you have your a rigorous model. So you have your, like, for example, your ice band or your symmetry models. Try to mimic the plant. Yeah, for example, you saw last week I showed you like a dynamic simulation of a DME plant, which, I mean, in a way, it's our process plant, and then we have the symmetry steady state simulation, which says like a rigorous model, and then from this rigorous model, we can also get the data, or we get data from the plant, and then together with the rigorous model's data, we then try to make some model. So that model typically, I mean, this graph basically only says that linear model cannot reflect the operations in reality, because it says that, well, if you have like a linear model, it will then just go straight. Well, what we want to have is something like this. Yeah, what we could do is then to try to linearize this as much as possible. For example, we know, say for example, this is then a kind of like what I explained in the hydrocracking unit example. So we have like a certain, so we have to divide this into like a certain operating window. Yeah, for example, these are your x variables, and then this operating window. So from here to there, so you can say, well, from here to there, this is then the model, right? And this is a linear model. Yeah, so for example, this is your x, and this is then your y, your y. So this is then your linear model. So from here to here, you can safely assume or safely consider that this is the linear model. So you use this linear model. So you can, and then from here to there, that's another linear model. From here to there, that's another linear model. So you have 1, 2, 3, for example, up until here. So for example, this is the new acceptable. This is the new acceptable operating window. So from this acceptable operating windows, you have like a 3 linear models to as a representative of your plant. Okay, so you use these 3 models as a representative of your plant, and then you then try to see where is this y becomes the maximum in that sense. So you model that, you put that into Excel or whatnot, and then you can see that based on this model, it will then say, well, this is then at this x, at this x, at this x is then your maximum. Indeed, if it's say even over here, right? So it's then your maximum y, and then you can see this is not that accurate. So then you have to then fine tune the model in such a way that this error becomes as small as possible. Yeah, becomes as small as possible. If it cannot be made any smaller, and so be it. At least we know the trend that the x has to be to the right. Yeah, that is much more important. The trend is much more important than the absolute number. But obviously, from the academic standpoint, from the from the procedure or from the working procedure perspective, we need to be able to as much as possible minimize the error between the model and the data, or maybe the linear model, and then the rigorous model. So the delta over here. Yeah, I'm basically explaining what this is. So we have, like, for example, so we're starting, so from we have this bold lines, so that's the process, and then if we start with the rigorous model, the one that we have already, so we the steady state model, yeah, for example, in our DME plan. So we then choose a certain feed that we know, and then certain operating conditions, and then we can then find the effect of the quality or the product yields or whatnot. So it's basically saying that what are the x that controls the y, what are the independent variable, sorry, what are the dependent variables that we want to monitor, that we want to maximize, or do we want to as our KPI basically, which is then in this case the product yield, for example. And then what are the independent variables that controls this y. Yeah, what are the independent variables? And then you have this simulation model, and then you can then make a sensitivity analysis as I showed you the other week, so that you can have some data on x and some data on y, from which you can then make a plot and then make how do you call it, like a regression model. Yeah, and then yeah, this is basically the sensitivity analysis, is step 2. And then you make the regression analysis. So I'm just now I'm just jumping from one slide. I'm telling the stories of 2 slides basically. So you can have like this yield, and then base yield, and then the delta. So in this case, what they mean is then this base delta method, which I forgot to mention. So they have for example this delta. You have this base case simulation model. So x o and then y o, and then you change the x into x1, and then you have from this x1 you have this delta x, right? And then from here from this x1 you can then get y1, and then from here you have the delta y, and then you can then make a connections between delta x and then delta y. So this is basically what they mean by this delta method. And then the equation is basically this one. So you have yield, you have base yield, and then yield minus base yield is then the delta yield, is then equals to coefficient, linear coefficients of this specific gravity, sulfur content, aromatic content, and so on and so forth. Yeah, so that's basically this example illustrates the yield, the delta yield against the feed characteristic, because you know this is a feed characteristic. But you could also say, well, not only the feed, I would also include the effect of operating conditions. That one you can do so. This is just an example where they try to see, given the current operating conditions, which you don't change, they just simply change the amount. I mean, change the type of feed. They get the data, and then they can develop these equations. Another way is that, yeah, I mean, this is just an example of nonlinear and a linear approximation. So, for example, if we have like a regress model which fits to the data, yeah. So in this case, regress model fits more to the data, and it says here there is a nonlinearity between the amount of hydrogen that we need, the amount of hydrogen that we need, as a function of sulfur in the feed. So and then you can see if we approximate this as a linear model, you can see that at the higher sulfur content, we are kind of like underestimating the amount of hydrogen needed. The same way that we are, if we are at the lower sulfur content, we are also underestimating the amount of hydrogen that we need. So in this case, we can either, like I mentioned, we can either slice it into several x equations, or we can say, well, I just want to operate within this range. Yeah, that could also be the case. Yeah, in either way, either you slice it into 3 different operating conditions like this, or you can just use, I just want to operate within this range. That could also be the case. Yeah, depends on what you want. Basically, depends on what you want.
This is fine.
Yeah.
I have confirmed with the chart that your voice is keep missing. Your voice is keep missing. So I don't know if you. I think it could be the internet issue. Maybe you can try to maybe turn off your video for a while and then see if it's solving.
Okay? Let's see. Yeah. Turn off my video. Keep so that we know my video.
And if it's still happening, then we can try other thing.
Okay. Is it okay?
For now it's okay.
For now it's okay. Okay, very good. Thank you. Thanks. Yeah. So everything that I've told you, so I'm just simply jumping all of the slides over here. So everything that I've told you is what they call. Now it's fine. Yeah. So it's what they.
It's still cutting.
Cutting. 1 minute. Yeah. Maybe I need to change. I need to change location. Maybe. 1 minute. Yeah. Give me one second. 1 second. One minute.
Actually, when you turn on the video, right, at least we know that you're cutting, that your video is frozen.
Oh yeah.
We know that. Okay.
Okay.
But if you turn it off, then we don't know.
Oh, okay. Yeah. Let me think.
Connection.
Let me think. A minute. Yeah. I will change location. 1 minute. Yeah. Mati. Now, how about now?
For now, it's okay. We'll see for a while. See, check.
Okay. Okay. No, I forget my mouse. I'll get my mouse. Yeah. Yeah. Okay. Yeah, this is just an algorithm that that you can look it up. Yeah, I mean, this is just like a simple math problem. Um, don't think we want to spend time here. This is one as well. Yeah, this is just simply an optimization algorithm that they use to linearize the non-linearity of the data or the model. Now, so how do they then decompose the problem? So we see that we have an overall problem where we have the oil refinery, and then it gets something, everything is in it. I mean, we have the feedstock coming, we have the catalyst, we have the heat, power, utilities, and so on and so forth, and then hydrogen as well. And we have a bunch of products, we have a bunch of products that we're going to produce. And then in this oil refinery, there are many processing units, right? There are many processing units, and then how do they then simplify this or try to solve this interdependency or the complicated problems in itself. So what they do typically, they divide it into like several decision levels. So if you remember in our first class, I guess we have the planning hierarchy, right? The management hierarchy, and then we have the scheduling, and then we have the optimization unit on the RTO, and then they have the DCS level. So you can still remember that one, right? And then in this case, they split this into two levels. So the management level, and then the operational level. So management level is basically they simply they don't want to see what's in it, like this unit 1, 2, 3, and 4 and 5 and so on and so forth. They only want to see if I have this black box, or not merely black box. So they have this unit 1, unit 2, unit 3, unit 4, 5, and 6. What they want to know is that what type of feedstock and how much power, heat, utilities, all of this they want to know that. And then in such a way as well, if there are unit dependency between this, in this case like unit 3 and to unit 4, and then or from unit 4 to unit 3 back, and then how things are connected. And they don't, or they cannot see, I mean, they split this into they don't want to see what's in the unit 1. Do you have any reactor, or do you have any distillation columns, or you have a different type of catalyst? They don't want to see that, otherwise it's going to be very complicated. So they just want to have like a high level overview. So this unit 1, for example, it is being characterized as I don't know, a type of a simple type of product. So if we have a feed A, feed B, and feed C, and then if we mix feed A with feed B in different ratios, they know already like a yield functions of those. So knowing how much is then the what type of feed and how much each of them, and then how much is in the power or heat, for example, for this unit 1, they can then calculate what are the typical outputs of this unit 1, and then use that typical outputs to enter unit 3. Yeah. So it's more like a very high level, and then based on the data that they have, they generate this linear relationship between in and out. Okay. And then they do the same for unit 1, 2, 3, 4, 5, and so on and so forth. Yeah. And then in the end, as a big box, they have like what they call like a refinery wide optimization. So that's where the term is being used. But in this case, if we move on, I mean, if we go into detail, is the linear model that they use in calculating this unit 1, is that correct, or how correct is that, or how accurate is that? So if we see in a, for example, yeah, this unit 1 is this guy. So unit 1. So this unit 1 is I don't know, in this case it's a simple distillation column, or maybe there's a reactor here and there, and then they know, well, we have to operate this unit, we need to know what type of feed, and then we need to know what is then the pressure, what is then the reflux. Where's the reflux? So here, where's then the reflux flow rate? So this reflux flow rate, how much is then the duty? In such a way, they can then tell, okay, we have this product 2, and then we have also product 1, for example. So they can then evaluate the linear model, yeah, this linear model that they have that is being used in that management level. So they can then validate this with the with their rigorous model of the distillation column, and then which they can also compare that with the data on the plant. Okay, so they have data on the plants, they put it into this model, and then that model will then they validate the model in such a way, the all of these constraints, like in this case maybe the activity of the catalyst, I mean the effectivity as well, or the efficiency of the trace, it can be taken into account, updated, and then taken into account to calculate how much is then the feed 1 and feed 2 given the type of feed that we put in, like in this case this row for example, and then the operating conditions. So for example, we have like feed coming in, right? So we have feed coming in, and then we have also like this then reboiler duty. So that means this then your utilities coming in. So you have your utility coming in, right? So this utility is also going into that unit 1, and then we have also like for example heat is then this heat, sorry, this heat coming in, and then the utility, maybe this is then the cooling water, I don't know. Yeah, we have this condenser over here, and then so given these three inputs, just take this input, the feed, the type of feed, the flow rate, and then the amount of energy that you used for the reboiler, and then the amount of energy that you discharge to the environment in terms of like a cooling water. You can then make a model between the product and then the feed. So it will be something like to visualize it. I will paint. So your model will be like, in that case you have unit 1, right? So your model is then, this is then product 1, this is for product 2, this that you have your feed, and then you have your reboiler duty, and then you have say for example feed A, and then this is also feed B, and then you have I don't know, that reflux ratio for example. So now you can then, based on the data that you have of the plant, and then you can then make a model. Product 1 equals to well, yeah, we use the delta base method if you know. So we have the delta product 1 equals to that A times delta Q times delta B times delta reflux ratio plus what was it again, C times delta FA, D times delta FB, and so on and so forth. So these equation depends on the data that you see. If it can be made as linear as possible, good few. If not, then try to linearize it as much as possible, as what we have seen before. Okay. Now, so I put this here. Because I took it from our legacy of the UMIS lecture materials in 2002. So they say for that slide, the current industrial practice as of 2002. So I put it 2002 because their current is not our current. Yeah, our current is 20 years later. So they say in 2002, from the we have a good links. We have good links between the control algorithms, which is then the plants basically later on, and then we have the process optimization model. So we have the process model which we can then use to optimize it. Right, the one that I showed you the other day, we have this DME model, and then we can then use that model to do an optimization to maximize the DME product, for example. And then if we have already the optimum independent variables out of the optimization problem, then we can then set it here. Yeah, and then that particular model, as of 2002, they say there's a little communication between the model that we have for the unit and also for the site-wide linear model. Because there's a site-wide linear model, it's because the plants is aging, and then we can quickly update the plants, and then updating this plant and then communicate that to the because people doing this is basically like economists, what they call economists, but they are also engineers, and then if the communications between these are not there, between the engineers over here and then engineers over there is not there, so it's going to be very difficult to have an updated model and an updated LP model. So in the end, you will lose some money. But nowadays, I mean, different companies do it differently, and then some companies, I don't know. I mean, they must have their own ways or to bridge these communications between the economists and then the process engineers on here, and then from here to there. Each of the companies, they have the different structure, and you can then simply develop your own structure. Yeah, the nonlinearities problem, they decompose it into two things. They have the site operations here, the site wide, and then they have also the nonlinearity here. So they do the same. This one, the one that I showed you earlier, they linearize it, and then this one, well, if you can linearize it, please do so. If not, and then you have to stuck with the nonlinearity. So we have to make sure that the process optimization software or the process simulation software, it can handle the nonlinearity very fast. Otherwise, we will then be stuck in optimizing this. It will then take a lot more time, more than necessary, or it's very impractical to do so if it's too complicated and too nonlinear. Sorry. Yeah, this is just a way that they do this. So the amount, so we have, as I mentioned, so to maximize the yield or the product, they have there's an effect of the feed conditions and there is an effect on the operating conditions. So in this case, they decompose it into two. So this is then determined at the site level, so they know how much is then coming in, right? So this is then a site level, and then whatever happens in between here, it's on the process optimization, in the process simulation level, where this one we don't take into account feed as a variable to optimize. So this is no longer an independent variable, so it is a given. So if where's the equations? Where's the equation? So keep it. So this is this. So this one is not. You have this model, but this number is fixed from the site wide. So your site wide, it gives you this delta f. From that site wide, it gives you this delta f. So this is no longer, even though this is like a variable in the model, but we don't consider this as an independent variables. We consider only the delta q and then delta rr as the independent variables. So we want to maximize p1. So what are the independent variables? This guy and that guy. These are considered fixed. Yeah, let me know if that is not clear. So that's what it means here. And then so I summarize whatever I said before into this. So your project as well, and then everything related to this refinery optimization or chemical plant optimization, this is then like a generic approach. Where's my pen? Like a generic approach. So you have if you have a plant data, good for you, right? Use that and then make sure that data makes sense. Yeah, so getting sense of the data, get the correct data, it is another type of skills that you have to have. Yeah, so once you have that data, and then you can then complement that the data with the process simulations model that you have. So together, the good data, and then process simulation data, the good process simulation model can be used to generate a lot more data for better understanding on how the system works. And then from this data, you develop linear regression model, like I mentioned, with the bounds, and then use this model to do the like an LP optimization, yeah, as a site wide, if you will. And then once we get this, obviously we have the optimum independent variable. So put this optimum independent variable into the simulation, into the process simulation model that you have. Put that put that here, and then you will then get the results from that simulation. You will then get the results, and then you can simply compare the results of that simulations and then with the optimization results, right? So the difference between them is obviously the difference between the linear model and then the difference between the difference between the simulation results and then the optimization results is then the difference between your process simulation model and then the how representative the linear model that you have developed. Okay, And then if they are like a bigger than a certain criteria that you have selected for yourself, and then you can then adjust the linear model in point 2 here. So we can then take a look again into the data, and then if you need to do this successive linear programming, so you you cut this nonlinearity into a bunch more linear models, please do so in such a way that you can make that nonlinear as accurate. I mean, you from that non-linearity you can then generate many linear models, and then from that you can then try to mimic the data or the plants as much as possible, to until the error between the simulation results and then between simulation results and then the optimization results is as minimum as what you expect. Okay. And then you could also see the trend. If the trend is about the same, I mean, if the trend is the same, it's just the order of magnitude. You cannot minimize anymore. So so be it. So what you know is that I need to know whether I have to open that valve or close the valve, right? So then you can then try how to call it, recommend that, and then to the people on the field, and then if they agree, and then it makes sense, and then you can then try that gradually, or in a small change, and then and then basically you iterate. So I take this for example. So if you have like a reactor yield that you want to maximize, right? You want to maximize. So we have the superstructure of here, superstructure of, for example, you have different units, right? Unit 1, 2, 3, and 4, and so forth. And then you have the linear. So it's basically the same. I'm just repeating this. So you have a linear combination, linear models for unit 1, 2, 3, and 4. And then you do that site level optimizations, and then you get your yield. You get your yield here, the yield of the LP. And then you get also the X. So you put this X over here, and then you can then calculate the new yield. So this yield and then the yield that you have over here, they have to be see, are they lower than the tolerance that you accept? If yes, and then you get your solution. If not, then you have to then again construct a new or modify the linear yield correlations. So that's basically so this flow sheet. This diagram is basically what this is. Integrated optimization is more like the same way. So you have the model, and then you use the model to optimize it. It's basically the same way. And then this is I'm simply repeating myself. So you have this, then the site level, you have the objective functions, and then you optimize it, right? And then from here you can get your how to call it, the X optimum, and then that X optimum you put it over here. Oh, sorry, this is then the fit. This is then the fit, right? So because the fit is then taken at the site level, so you get your fit to maximize a certain yield, and then you put that field in here in the process level optimization, and then you get your X, and then that X is then comes back to the site level to see how different they are. If they're different, and then you either have to improve the site level model, and then the process is repeated. Otherwise, this process level optimization as well, this is the process simulation model, you could also improve that to match the data that you have. So it's basically the same way, the same thing that we have been repeating over and over again. So now refinery wide. So I don't know if there's any question. So this one is basically the example from Gurobi that I take. You have seen all of this, this whole stuff on the refinery. Where's that block diagram? Now this block diagram. So what that model says is that they have done this. This is done behind the scene. So different operating conditions or different feeds, they will then create different yields of products, and then that yield function is then put into here, and this is then the model that Gorobi example that we're going to see, which is here. So now assume that you have like a crude 1 and crude 2. We have crude 1 and crude 2, both have different characteristics. And then we have existing units. Here we have the distillation unit, and then after that you have like a reforming unit, and you have a cracking unit, and then you have like a gasoline blending system, and then jet fuel blending, fuel oil blending, and then lube oil processing. And then they have this 1 2 3 4 5 products. Okay. um, and each of these, they have yeah, I mean, for example, in this case, the light naphtha coming from the CDU, it can goes to reformer, or it can go straight to the blending gasoline. And then the same way with the mid naphtha, it goes to the reformer or it goes to the blending. The same way with the heavy naphtha, this then the light oil and the heavy oil, it goes to the cracking, it goes to the jet fuel blending, it can also go to the fuel oil blending. So all the configurations are there according to what you see on the plant, and these are, like, for example, the important product streams that you have to evaluate to maximize your profitability of the plant. This is the data, so we can see we have two crude, right? So crude 1 and crude 2, and then the availability, crude 1 and crude 2. Crude 1 is maximum you can process only 2 kilobarrels per day, and crude 2 is only like maximum 30 kilobarrels per day. And then can I put like maximum? No, you cannot put maximum, because the distillation unit itself maximum is 45 kilobarrels per day. So you have to choose either crude 1 or crude 2, and how much, in such a way that you make you don't cross this maximum limit of CDU. And then for each of these group 1 and group 2, we have different product yields, light naphtha, medium naphtha, and so on and so forth, until residue. And then we have the associated octane number for these naphthas. So this is the distillation data. So I mentioned here distillation data. So this is then the data in this unit. So you know what's coming in, you know what's going to come out given a specific flow rate, and then you know what is then the quality of these products, right? And the reformer naphtha, we have reformer data. We have also maximum flow rate capacity of naphtha. And then for each of these naphtha, for example, if you have like light naphtha, and you will get so if you have like a light naphtha over here, it goes to reformer, you will then generate like a reformed gasoline. So reformed gasoline, and that reformed gasoline is as much as like how much is that? 60%. Yeah. So 60% of the light naphtha, it goes you can produce reformed gasoline, which is a lot. And then the heavier that you go, the lower the amount of gasoline that you can produce, which makes sense, right? So these are the yields number. So it's basically like right, so we have dy, which is then the yields, and then equals to 0.6 of the light naphtha. So it's very straightforward linear regression. And then this yields the reformed gas gasoline from the light naphtha. It has this octane number, the same octane number for all of for the reform met gasoline. We have the cracking data as well, so you can see cracking data. So this is the cracking unit. So we have like a 1 and 2, light oil and a heavy oil as the inputs, and then from this light oil, heavy oil, we produce two valuable products. Yeah, here the only valuable products that they want to consider is the reformed gasoline. There are other products, but they don't consider that into account, so simply because of the economic of those products. And then in this case, we have two products: the cracked gasoline and then the cracked oil. So cracked gasoline goes to the gasoline blending, cracked oil goes to either jet fuel blending or fuel oil blending. That is this one. Okay, so we have light oil, and then we have light oil, we have heavy oil. The amount of cracked oil produced, or the yield of cracked oil, so it's a barrel per barrel, or yield volume, 0.68 of the cracked oil if it's produced from light oil, and then 0.28 of cracked gasoline if it's produced from light oil. And also you can see that the data makes sense. Okay, and then in this case, if you put like gasoline, you only end up with 105 of octane number. And then the blending data, yeah, there are lots of data that you need to fulfill. So regular gasoline has to have an octane number of 84. Premium gasoline has to have an octane number of 94. So you have to mix, you have to be able to mix, right, at this part. So once you produce how much this, how much that, how much this, how much this, how much that, and then we have to be able to produce to make regular gasoline or premium gasoline. Both have different octane number. That's one. And then there is like a sales requirement that you have to produce gasoline 40% more than the regular gasoline. So that's like a requirement for sale. So that's we also take that into account. And then the jet fuel requirement, we have this vapor pressure, and then the light oil, heavy oil, crack oil, residue vapor pressure. So they have their own vapor pressure. And then if you want to blend them in the jet oil, see that jet oil blending. So we have light oil, we have crack oil, we have the heavy oil, and then we have the residue. Each has their own specific vapor pressure, and then there is a limit of this vapor pressure as like a fuel spec for the jet fuel. So it has this one. Okay. And then fuel oil to blend should be in the ratio blah 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 blah. So this is done. We everything, because this is then the as you will see, this is the most important product, sorry. And then this is that like a remaining, yeah, gasoline and jet fuel in this case. Okay, so gasoline and jet fuel becoming the two most profitable products. And then this is simply if there is anything left goes to here, or and then if there's anything left goes to there. Yeah, we have this residue data, and then this is then the profit contribution, you can see. So the gasoline is, sorry, this is the gasoline number, this is then the jet fuel number, this is then the fuel oil number, this is then the lube oil. Okay, and there's also like yeah, lube oil production. So yield is this one, and then the lube production should be in between this one. And then the question is that which the question is that simply which crude to process, and then which how much of these streams, how much of this reformat gasoline, and so on and so forth, in such a way that we can then maximize the profit of the plant. Yeah, the question is again, the question is then which crude to process and how much, given the current existing configurations of the plants, given the current process performance, which is all those yields and then those run number and so on and so forth, in such a way that we can then maximize the profitability of the plant. So that's a very simple problem. But getting all of these numbers, yeah, indeed, I mean, once you get all of the numbers, once you make this flow sheet, you get all the numbers like this, right? It's just a matter of mathematical modeling and optimization. So it's very easy to do. But in reality, the most difficult one is then to get to know these numbers, yeah, to make sure that these numbers are acceptable, these numbers, that numbers, these numbers. So all of these numbers, making sure that they are consistent and then they are acceptable and then agreed based on knowledge of the people that the people have. So getting those data correct and consistent, that's much more difficult than developing the mathematical model that we're going to see, and then we optimize it. Yeah, okay. So don't get me wrong. Okay. So this is the Excel model. You can then click on it, and then I have it open already. Where is it? So I have it open already. I don't know if you can see this. So we have code 1, code 2, and then the maximum flow is 20,000, 20 kbd, and then it's also 30 kbd, and it goes to code a CDU, and then we know that the CDU is that maximum 40 kbd. Okay, so this is then the maximum number. And the question is then how much is then the flow of code 1, code 2, and how much is then the flow of code 1. Okay. And then so you can then, I mean, I can then just, delete this and then delete that if we don't know, or maybe this is then 1, this is 1, I don't know. So 1 and 1 makes it 2, and then you know that yeah, 2 is much lower than this 45, so you could increase more until you reach this 45 kbd. But nonetheless, if we have this like a dummy, so because since, for example, we don't know how much each of the code, it's a dummy code, and then you put all of this data into these calculations. So we have the yield of you use code 1. These are the yields. So these are the data that you have for each of these light naphtha, medium, heavy, oil residue. yield of crude 2, and then this is then the amount of barrels per day of each of the products given the crudes and the yields. So for example, you can simply model this like yeah, it's a straight mixing, right? So crude 1 yield, crude 2 yield, and then plus them, and then you can get your barrels per day for each of the product streams. And then this residue is basically this number. So this number is this number. Okay. And then you can then, yeah, separate them into, from this light naphtha, for example, it can go to the reformer, right? And then it can also go to the straight to the blending station. So this blending station, and then you can make this what was it again? Yeah. So so we have, for this reformer, you also have this maximum 10,000 and so on and so forth, and then you have the yields of the reformer for each of these for each of the feed, right, for the feed. And then the octane number is 115 for the reformate, and then in this case the flow is negative because I just put like 1 and 1. So and then you can see, so I put the price, and then this, then the minimum octane number for this regular gasoline, and then the minimum octane number for the premium, it goes to 138, and so on and so forth. So the profit is then in this case 72,000. Okay, but they are all like still, this is not a feasible solution in a way, because there are many negative flow rate, which is not correct. But nonetheless, you put all of these mathematical equations in the Excel or in whatever you want to put in. Like for example, we could also, if you go to that Gurobi website, they'll show you all the mathematics, and then so then you can you can code it in Python, for example, in this case. So you code it in Python. It's here, yeah. I'm not going to repeat it for you. So you can look it up and then see how things are being calculated, right? So and then they make the models, and then they so they have the constraints and so on and so forth, and then they optimize it, yeah. So they make it maximizing the objective function, which is then the profit, and then we can go to profit. Sorry. Profit is where's your profit? Where is that profit? Yeah, anyhow, somewhere here. Just look at this and then see if you can find it. If not, then let me know. Product, and then octane number, constraints, optimize objective, and products, and profit, and product profit. So you have to look for this data and then maximize, and then using Gurobi, and product profit, and product profit. We have the end product. We have the end product variable. End product. Yeah, somewhere. Okay, anyhow. So you go back. So it's all modeled here in this Excel, and then you can simply use the, sorry. So I make it here. Hey. Right, so we have the overall plant over here as a site-wide optimization unit, yeah, site-wide optimization unit, and then you can then say, now I want to solve this. So all the constraints are here, and then we want to maximize A49. Sorry, close. So A49, AM49, which is this. So total profit. So we want to maximize the AM49. What are the variables to change? So in this case, all the variables to change is then the flow rates, how much then this flow rate and that flow rate, right? Because these two are independent variable, and then how much is then the light oil that goes to the cracking, and then the heavy oils that goes to the cracking, and also the light oil, heavy oil, and then cracked oil that goes to the in this case to the jet fuel blending, and then how much is then the light naphtha, mid naphtha, and so on and so forth that goes to the gasoline blending, and then the rest goes to the reformer, right? Because where's that flow diagram again? So if you then, for example, if you put this one, and then you can calculate this based on the yield functions. But then from here, you need to send this to either reformer or gasoline blending. So use one as an independent variable because it's a valve that you can just open and close, and then the other one being like a dependent variable. So this stream is calculated by this minus that, right? So this stream is this minus that, and then this then your independent variable, and then this one is calculated from how much this is and plus how much that is. So that's basically what this is. So there are a number of independent variables, right, here, and then put all the constraints, and then we know this is non-linear because of the mixing, and then we can click solve. It will take some time. It's a feasibility bounds somehow, and then we can then click cancel, and then we so now, for example, if I put like I don't know, maybe if I put like a 20, sorry, this is the one. So here you have to because of this is non-linear, you have to put like a good initial value. So 20,000, and there's also like 20,000, and where's that stuff? Maximize it. Now you get the solutions, right? So the solution is that $200,000 per day is then the maximum profit, and then in here you can say, well, I'm maximizing the code number 2 while minimizing code number 1. How so? So you can see here, so code number 2, it will then yield a lot more mid naphtha. It will yield like, I don't know how much this is. If some this about 60%, right? 58%, and if you sum this, so we have only 50%, so we have 8% more of naphtha produced from crude 2, right? And then we know that this naphtha, it goes to the reformer and then gasoline blending, and then it costs like the highest number of price, $6 per barrel, and also $7 per barrel. Okay, so from these cost figures, we need to maximize gasolines as much as possible, and then if there is any extra, and then it will then go to the jet fuel, and then to the fuel oil. So this is then one case, right? So you can then say, for example, copy, so you can this is then base case, this is then your, I don't know, gasoline, sorry, this then gasoline is more expensive, and up to you, yeah. And then from this base case as well, you can then say, okay, now if, say, for example, well, somehow the jet fuel price is increasing, so it's no longer 4 but it's 5, for example, or maybe I don't know, let's see if it's 5, and then how much is then each of these what is that stuff, solve again. So now your profit is then 22,000, obviously, 220,000, and then the this is still, you produce still the same. I mean, you're using the same amount of crude. Let's see if there's anything different. let's see, for example, this gasoline, yeah. So this is how much that goes to if there's anything different. So this one compared to the other guy, you can see yeah. So at the higher jet fuel, this is the cost. This is the results. So at higher jet fuel, you would then see this gasoline. Yeah? So at sorry, right, so at the if the jet fuel price increases by like from 4 to 5, that means 25%. If the price is increased by 25%, you see that there are some changes required for the gasoline blending, yeah, because we are comparing now, for example, in this case, gasoline blending. So the more the 25% more jet fuel price, it seems that you have to then send 6,000, so about, yeah, 5 times more of light naphtha to the gasoline blending, and then it's you minimize the medium naphtha by like I don't know, maybe 30% lower, and then the heavy naphtha is constant, and then the reform gasoline, it goes like half roughly, yeah, right, half for the regular, and then the premium, you have these differences. So you can then by showing this, and then making a, I mean, you can change your case, yeah, different prices, and then what else, because that's the only thing that you that is then dynamic. All of these yields, they are not to be changed because they are the characteristics of your plants given the feed that you are going to process. So we're not going to change the yield numbers. So the price number is then typically what people then change given the dynamic of the situations. So they know what they produce. So for example, let's take another one. If if the price here is higher, so we would expect then the jet fuel is then the higher. Let me copy this, then copy, so that I can see this is not base case. Jet fuel 20% expensive, right? So this guy, so it makes 15 kbd for the more expensive jet fuel, and then it's also 15 kbd for the same gasoline. So it doesn't really matter apparently. Yeah, after long explanation and evaluations, apparently the amount of jet fuel being produced is not that much. But then if you get okay now, because this number is smaller than this and that one, yeah. So you can play around with this, yeah. Let's do another round. Let's do another one. For example, it goes to like I don't know, maybe this one is then the gasoline drops. Say for example, we want to make, I mean, minimum, because premium is then minimum 40%. Say for example, the price is changing and the situation is changed, and then nobody wants to buy premium anymore. So in this case, you can say, well, premium is not 40% more than the gasoline. Not 40% of the gasoline, not 40% of the gasoline, right? 17,000, so 7,000, so it's not 40% of the gasoline. So regular, okay. So maybe like I don't know, maybe 20%, because it's not much of a request, and you can then say, yeah, see what happens. Now you can see the amount of jet fuel produced is still the same, but then they put more into the regular gasoline, okay, than the premium gasoline, because of that situation. And then you can change this, for example, I don't know, change more the price. You can do whatever you want, yeah. I mean, this is just an example to show you what we could do once we have the model. And then from here, now I just want to make a connection from here, for example. Say now this is then your site-wide level optimization. And then okay, now in this base case, for example, in this case, so we pick out of these three cases, we pick this case. I don't know what this case is. So we say, well, the reformer will have to the reformer will have to treat like 4,000 kbd, 4.4 kbd. Yeah, so that reformer will have to treat 4,000 kbd. So these numbers becomes a fixed variable in your reforming optimization. Yeah, so you have another model for the reformer in the process simulation, which is much more detailed than it is, because this is simply like yield number. So that reformer simulation, you have to fix the feed flow rate, and then you can then fine tune how much is then the severity of the operations, the pressure, the space velocity, the temperature, the recycle, and so on and so forth, in such a way that you maximize the profitability of the reformer itself. Or maybe you want to maximize the in this case, for example, maximize the reform gasoline, because here the job of this reformer is only to produce this reformate, right? So once we know this, once we know that, once we know these three streams coming in, the detailed model of reformer, its job is only to maximize the amount of reformate gasoline in such a way that it goes to the gasoline blending, right? Because if you produce more, this will then we can always make more. So but then what are the operating conditions necessary for this to happen? That is then the process level optimization. I hope that is clear. I've been repeating myself several times. If not, then let me know. So that's basically the examples on this, and then you can solve it with Ruby and Python and so on and so forth. I put the code here. You could also go to the website, and then they give you also the code. So this is then the refinery debottlenecking. So this is what I meant by if you can remember, I put here, this is for next week. Hey, sorry. Not debottlenecking. So this is this one. We will discuss this next week in our last class. Now plant debottlenecking is this one. Okay, pioneer debottlenecking is the same. So we have 40 minutes to go. Now suppose that we there is like a 10% market demand. Suppose that there's 10% market demand on certain products, right? So 10%. So that's a requirement from the sales and planning. And then they say, well, we have to make this 10% more. And then what people typically do, I mean, I don't know what is being typical or not, yeah, but if you can imagine, one of the alternatives, well, if they need more 10%, and then you have to put more 10%, right? So more crude to process, which, well, in a way, it makes sense. You want to have 10% more output, put 10% more input, like in this case, right? So this case, so you want to have like a 10% regular, so 10% more of this, well, you can have to put 10% of that, as simple as that. And then they do the simulation. They know how much is then the input, and then they can then redo the simulation to get to the new throughput, and then find the bottlenecks. For example, in that example, maybe this is then the bottleneck. You know that to get like 45%. So yeah, for example, so this guy, they want to have like a 10% more, 10% more, for example, and then that means we have to include this by we have to increase this by 10% more, and then we know that this is then 45 kbd, if you can still recall, and then 10% more means it has to be like a 50 kbd, right? So that means this is then your first bottleneck. This is then your first bottleneck. So you need to relax this. Means you either increase the distillation unit capacity, or you can just simply plug in by a new smaller one. So up to you. Yeah, there are many things to do that. So that's an alternative to do so. And then find the possible bottlenecks and then relax them, and then evaluate the profitability if you relax this and that and this, and then you can then revamp it, install new CDU, for example, and a new FCC or whatnot, and then you can get your debottlenecked plant. Okay, so that's an alternative of doing it. But then what is then the smarter way of doing that? So a smarter way of doing that, we simply go back to your Excel file, right? So we need to understand the existing plan. Understanding the existing plan means we understand how the mass balance around the plant. Yeah, you know how the oil flows, the hydrogen, energy, and so on and so forth. You have that Excel mass balance and then the process simulation mass balance model. So you have two models as you have been seeing now. And then you simply that yeah, this case, well, generate and evaluating the bottlenecking options and then implement it. So to do this, we need to have like an accurate representation enough for the plant, like what we have in the Excel file. And then we can then simply consider the operation variations and then do the optimization. Say for example, sorry, no, before we go to that, because in the end, so it says this for example. So now I don't have to say for example. So this vacuum gasoline, it can go either to hydrocracker or FCC unit, right? Hydrocracker or FCC unit. And then where does it go and how much, right? Either it goes to here or to there or 50-50 or 60-40 or 40-60 is something that we need to find out. So we cannot just simply say, for example, if this is then they want to have this by 10%, that means we have to increase this by 10%. That is then the alternate, well, an alternative that I mentioned. But now in this case, we can then play around once we understand how the plan works, and then we can then play around how much is then the gasoline that goes to vacuum gasoline goes to hydrocracker, and how much is then goes to the fluid catalytic cracker. Because in the end, what we need is only higher profits, right? What we need is a higher profit. It does not necessarily mean, say for example, if they say, well, we have a 10% demand increase in a certain area, that doesn't necessarily mean that we will have to provide that 10%. You can follow? Okay, say for example, in this case, so if it says they need to have like a gasoline 10%, right? For example, in your area, that doesn't necessarily mean that your plant will have to produce that 10%, right? Um, it can be done by somebody else or whatnot, but then your goal is simply to maximize your profit, either by fulfilling that additional 10% or simply by rearranging the streams as what we have been seeing in such a way that your profit, no matter what the economic situation is, your refinery is always profiting from from its operations, right? So you don't need to produce all products, you don't need to satisfy all demands. If those demands are like in contract base, yes, obviously you have to fulfill that contract, but then the rest of the products, the rest of the streams, you can do whatever you want in such a way that you maximize the profitability of the plant. Yeah, and then from that you generate the alternatives. Yeah, you can go here, you can go here, you can go there, so up to you. But the bottom line is that you don't need, I mean, it's not necessary for you to fulfill that 10% increase. Your goal is then to maximize the profitability. So yeah, instead of increasing the feed by 10%, you could also say, well, explore all possible destinations. This one is basically saying that you have to make your own mass balance. Okay, your own mass balance, the one that you have already. So if you have it already, fine, good for you, you skip this option. If not, then you have to make it. And then if necessary, right, for example, you can also like purchase cheap intermediate products, right? You can purchase this, or you could also like sell expensive intermediate products. And you don't need to sell, I mean, you don't need to blend, for example, I don't know, you don't need to put that like in this case, what is that stuff? Wait, in this case, say now, uh, suppose is that if this heavy naphtha is required, for example, right, and then you can sell it with the higher price, for example, it's not necessary for you to send this to reformer. Yeah, just simply to meet like this 10% increase, because what you want to do is then to maximize your profitability while still obeying the contract that you have. But then you can also say, well, I can fulfill the contract by mixing this light naphtha and and mid naphtha, and this heavy naphtha, for example, I can just simply sell it because it has a higher price somewhere somehow. Okay, the same goes with the with this say for example instead of like buying crude 1 and crude 2, there is a residue somewhere. So there's a residue somewhere which you can then send it to your jet fuel blending, because this residue maybe it's cheaper than this crude 1 and crude 2, or maybe it is a little bit more, it has a better properties than this guy, so hence you can buy this cheap residue somewhere, or cheap naphtha or whatnot. So these are the things that you can consider, the alternatives that you can consider, and you put that into the existing equations. Okay. Yeah, so what else? Yeah, I hope you understand. Yeah. And then for example, you could also do like a case here. For example, if you can do so, say that for example we because this new area, I mean this new demand comes from a new area where we don't have yet the market share in that area. So because of the situations, okay, we will then try to make to meet that demand. For example, in this case, we go back to this. This was 4, right? And then this was like a 40%. Say for example, in this case, this was the base case. Right, so I need to rerun this. So as a base case. Right, so this is then your base case. Because the 10%, I repeat, that 10% comes from the area where you don't have yet a big market share, and then you want to fulfill that demand simply because you want to get that market share. So what you could do is that, well, say we still have to maximize the profit, but say for example that they need to have like a 10% demand more on the premium. So that means 10% of this, maybe 45%, right? So sorry, 10% of this 40%, 10% of this guy means about I don't know how much this is. 10% of this is 600 somewhere, 700. So if we say, well, so that means I need to make like so this minimum. So we say, so this has to be like a minimum, like a 10% more. You can say 10% more. So now you have that into the equations, and so now you put that. What is this? Oh, this is just to facilitate. So now you have so you need this to be like because suppose that this is 7,000 and 10% one is 7,700, suppose, yeah, just to make it or 7,500, and then you can add the constraint here. So this guy has to be sorry, now I'm now close. Or am this is then the objective function, and then you add a constraint, and this constraint says, well, this has to be minimum, for example 7,400, 500, right? And then that's a new constraint that you say that you put 7,500, this guy, right? Because we need to fulfill that market for the premium, and then the initially we have this 211, and then you can then click solve, and yeah, it's not much 211, but then you are making this you're fulfilling this barrel per day. And then what is this? Yeah, let me see. 40%. Oh, 40% of this. Okay, so this is if you produce 40% from the, I mean, this then your previous constraint. So 40% of the regular gasoline is this number, but now your premium gasoline is 7,500 instead of this 6,500. So it's this is then the amount of I mean, that's how you do it basically. Yeah. What else? Yeah, there are also some options well known in this chemical plants or refinery. So we can also shift bottlenecks. For example, in crude in the crude distillation unit, you have this heater, upstream. And then from that, before that heater, you have all of these heat exchanger network trains. And then you can say, oh, if I want to increase the crude capacity, my furnace is then the bottleneck. So I cannot buy, I have to either buy a new furnace, or yeah, simply buy a new furnace. So they because that's the only option, for example. And then you could then think, well, instead of revamping this furnace, see if I can reroute some of the energy streams. It means you can revamp the heat exchanger network in such a way that you try to avoid relaxing the furnace. Yeah, revamp the heat exchanger network. So that means you do heat exchanger network study or pinch analysis study on your crude preheat train. This is the one that I have mentioned before. For more profitable products, direct revamp or alternative, or less unprofitable products, so you can either direct revamp or upgrade the products. These less profitable products, you upgrade it to higher value products. So there are many alternatives, many options that you can consider. And then once you have those options, right? Once you have those options, you can then make a rank like this. So we typically, I will tell you, for Max, there was a situation where people who do this, they are in the project management department somewhere somehow, and then what they do, they don't have like a system on how to evaluate the project management. Means they don't know which project to prioritize and which project to sacrifice, right? Given the budget that they have. So so they came to us, they came to me, and then they say, well, we have this problem. And then typically we do like a gut feeling kind of approach. So if one person evaluates that project, he will then select project A, B, C. And then if the same problem goes to project manager B, and then he will then evaluate that based on like C, D, E, F, G, and so on and so forth. So there is no like a clear guideline, all based on experience and gut feeling on which project to prioritize. So an approach here is that basically what this says is that you make like this kind of curve. So you have you have 7 projects, right? In this case, 7 debottlenecking projects. You created 7 options, and then you then put them in the ascending order like this. So the first option is then this is in the $4 million, and then the last option is then 39 million dollars, and then this then the revenue. So this revenue is going to be also like the NPV or whatnot. Sorry, this is revenue increment, or you could also calculate the NPV and then investment. So so this revenue and capital, so this capital is then the investment. They make it like this way. So for example, they have like a 4, so this is then the 4 capital, so this is then 4, right, million, and then the revenue is then increased by 10. So here, so this is then that guy, see, this 10. And then there's another one, it has like a 10, and then this 10 is this is then the 10, and then this is then the 11 something. So this is then the second project. So they make these staircases in such a way that they can visualize this, and then they can then choose which project is then that they have to move forward. And then yeah, they can also do this like NPV calculations. Yeah, NPV calculations. So they calculate the first year, second year, third year, and so on and so forth, to give the signals which investment that they have to go through. I'm not okay. So what I'm about to say, from the example that I mentioned, those project management department somewhere somehow, if you go to there's also, I think it's beyond the scope of this class, but if you go to you Google something called like a financial pinch, something called financial pinch, and then there they showed you how to evaluate basically, or how to prioritize which project within a certain budget. Yeah, so what they do basically is so for example, so what they do basically is don't save. So so that financial pinch is also based on the pinch study, right? It's all pinch stuff, but it's very, it's a very powerful tool just to give you like a baseline and then things to discuss and consider. So what they basically do, we have the investment, right, the capex, and then we have also like uh, project A, B, C, for example, and then yes, capex is then I don't know 100, 150, and we 80, and then this then they like a NPV. I don't know, maybe this is then the 200, and this is then maybe 160, this is maybe 150. So this is the NPV, and then here, so this is the typical data that you should have, right, that you should have being a project manager. So get this data, and then they also consider in that tool, if I can still remember that they can they do like payback periods, right? So so in this case, for example, you can quickly calculate. Yeah, I mean in this case they have like very rough. So you out of this money, or return on investment, sorry, return on investment. So so this then the 100 minus divided by 200, right? So 150 divided 160, 80 divided 180 divided by 150, and then they rank it. So it's like a half. This is 150 divided by 160 is I don't know 0.9 something, and this is then the like this then a little bit more than a half, right? So half plus something. So they rank it in a way that they can then see. So what we did at the time, we have like a budget. This is our budget, and then this is then the slope between the NPV, sorry, capex and an NPV, capex and NPV. So that slope is this one. This is then the project. So this is then the order. So order number, this number one, right? Return on investment, the shortest one. So this one, this is two, this is three. This is project one, two, three, and then this then the project one, this then the project two, and this is project three, for example. So the slope is basically your the ROI. So if we have this amount of budget, so you can say, well, I will have to prioritize the project number one, which is this one, prioritize, and then for project number two, I don't have sufficient budget because I have only this than the budget that I have, and then project two, I need this additional budget. So I will then from out of this pocket we can finance this project two, but we need to have this delta extra by loan somewhere, right, for the bank or whatnot. So in this case they know, well, project one is the top priority, I mean the priority one, and then project two is in the second priority, and then this we cannot finance completely 100%, so we have to borrow from someone else. And then this project three, given the I mean the interest rate or whatnot, so you can evaluate whether you want to finance this project with the third party, or you still want to go ahead, or you can just simply stop. So we don't currently this year we don't have a budget, so we will then remove this out of the list. So this project 3 is off the list, and then this year or next year we'll only do project 1 and project 2. So as simple as that, and then you can learn this in that financial pinch article. Okay, so last slide. So good that we finished this before 2 hours, so you have some questions. Now summary. First and foremost, you cannot avoid the first principle of solving any problem. Number one, that first principle is to understand the problem. So your plant is your problem, so you have to understand your plant. You understand the existing plant, explore the interactions between all of these equipments and streams and whatnot, which means by extension you have to make the mass and energy balance for your plant. Yeah, there is no escape. And then if you want to do like a debottlenecking, so you generate the options and then you can then calculate, like I showed you. You can calculate the economic investment and then make a priority, and then you will then implement that. So that's the summary. Well, it's I think you know this already, but nonetheless, I showed you what I can share from this perspective, from this course perspective, what we have to do, what we can do, what we have to do, and then do you have any questions? We have like 20 minutes less for question and answer.